In this section, we're going to talk about how to find the mean and the standard deviation for a binomial distribution. So it's actually much easier than just any probability distribution. So remember when in section 5.2, we had formulas and we had a way to do it on the calculator to find the mean and the standard deviation. Now, if we have a binomial situation, we've got very simple formulas. So we normally know two things. We know n, the number of trials we have in our binomial distribution, and p, the probability of success. Now, the mean, the average, you just take n and you multiply it by p. It's just n times p. The standard deviation is equal to the square root of n times p times q. And just a reminder, q is always equal to 1 minus p. Okay, so these are very easy things to find. Okay, so remember, we're going to use this for our range rule. So remember, our range rule told us that the usual maximum value would be the mean plus 2 standard deviations, and the usual minimum value is equal to the mean minus 2 standard deviations. So anything outside of those are considered unusual. Okay, so our first example says that 10% of the general population are left-handed. Okay, now, we normally would do this in a normal class, which we don't have, but let's say we have 25 people in a class. Okay, so first let's figure out what the expected number of left-handed people in the class would be. Well, it would be the n, so we're doing 25 people, and the probability of being left-handed is 10% or 0.1. So we'd expect about 2.5 left-handed people in the class. Now, the standard deviation would be the square root of n, so 25 times p, which is 0.1, and then q would be 1 minus 0.1 or 0.9, which ends up giving us 1.5. So the usual range of values, we would take 2.5 minus 2 times 1.5, which would give us negative 0.5 people, so we wouldn't expect any less than 0 anyways, but up to 2.5 plus 2 times 1.5, or about 5.5 people. So 6 or more people would be considered unusual. Okay, now, can we answer if our class is within the normal range? Well, I don't know how many people out of this made-up class are left-handed, so we'll say sure. Let's say there were 4 people who were left-handed. That would be in the normal range. Would it be unusual if just one person in this class is left-handed? No, because the usual range is between negative 0.5, which in all practicality that would be 0, up to 5.5. Okay, and on the next page it asks, would it be unusual if 6 people in this class were left-handed? Well, yes, because the max was 5.5, so 6 is bigger than that. Okay, so our second example says couples are trying to pre-select their baby gender. So before they get pregnant, they want to know whether they're having a boy or a girl. In a test of couples trying to have baby girls using this microsort method, 175 of 300 babies were girls. Okay, so now we want to think about what would happen if no method was used. Just they weren't using the special method, they were just naturally having babies. Okay, so if 300 couples naturally having babies, would that be binomial? Well, sure. We've got a fixed number of trials, the 300 couples. The trials would be independent. Whether one person has a girl doesn't affect the next person having a girl or a boy. There's success or failure. So unfortunately here, girls are success, boys are failures, just in this problem. So we can set it up. And then the probability of girl, we would expect each time to be about 0.5. Okay, so the mean number would be n times p, which would be 300 babies times the probability of girls 0.5. So we would expect about 150 girls. The standard deviation would be the square root of 300 times 0.5 times 0.5. which gives us 8.66. Okay, so the usual range of values, well, we would take 150 minus 2 times 8.66, and that gives us 132.68. And then we would do 150 plus 2 times 8.66, which gives us 167.32. So, is 175 girls out of 300 considered unusual? Yes, because it's outside that range. It's bigger than the 167. So what would we conclude then? We'd conclude that it would be unusual for it to happen randomly. So we can assume that the microsort method is working. So it is working to have a better chance at having a girl. Okay, and our last example, which should be labeled number 3 instead of number 2, says in a past presidential election, the actual voter turnout in a town was 61% of those eligible to vote. So that's we know who showed up. So it says in a survey, a sample of 1,000 eligible voters were asked if they did vote, and 688 of them said yes. Okay, so if these 1,000 people were chosen at random, would this situation be binomial? And the answer is yes. We've got a fixed number of trials. They either voted or they didn't. The trials are independent. And each person has a 61% chance of voting. Okay, so the expected number that did vote would be our n times p, which would be 0.61, or sorry, our n is 1,000 times our probability of 0.61. So we'd expect about 610 people to vote. And the standard deviation would be the square root of 1,000 times 0.61 times 0.39, which gives us 15.42. Okay, so if we wanted to figure out what the usual values from the survey would be, we would take 610 minus 2 times 15.42, which would give us 579.16. And we would do 610 plus 2 times 15.42, which would give us 640.84. So is 688 voting within the usual values? No, it's outside. It's bigger. So this would be unusual to get these results. So what conclusions can we draw? Well, either one, it may not have been a true random sample. Or the people in our survey, people don't want to say they didn't vote. They don't want to be looked down, so people may have lied. Now, it could just be that we had an unfortunate sample, but those are two things we could suspect.